Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good day to everyone. Okay, so basically today we will discuss on continuation from last video. Okay, so basically today the topic is also in second law of thermodynamics, whereby this is a part 3, and in part 2 we have discussed on the Carnot cycle. So today we focus on entropy, or the process isentropic. Alright. So entropy. So the second law states that process occur in a certain direction, not in any direction. So it often leads to the definition of new property called entropy, which is a quantitative measure of disorder for a system. Entropy can also be explained as a measure of the unavailability of heat to perform work in a cycle. This relates to the second law, since the second law predicts that not all heat provided to a cycle can be transformed into an equal amount of work, whereby some heat rejection must take place as well as maintain the equilibrium temperature. So the entropy change during a reversible process is defined as, so this is your equation. So change in entropy is change in heat divided by temperature. Okay, so for reversible process, for adiabatic, so we got your change is 0, whereby your S2, the final one, is equal with the entropy at initial state. So this called the reversible adiabatic is also called as isentropic process, because we have the same entropy. So this is for irreversible. For reversible adiabatic, so your final entropy is equal to initial entropy. Entropy change and isentropic process. The entropy change and isentropic relation for a process can be summarized as follows. So pure substance. At any process, change in entropy is equal to entropy 2 minus entropy 1, whereby for isentropic process, S2 is equal to S1, entropy 2 is equal to entropy 1. For incompressible substance such as liquids and solid, so at any process, S2 minus S1 is equal to C, specific heat average, temperature 2 divided by temperature 1. And your isentropic process is temperature 2 is equal to temperature 1. This is for incompressible substance. Okay. For ideal gas, so a constant specific heat, which is approximate treatment for all process, this is your equation. You can refer back to chapter 3. Okay, for isentropic process, we got this figure. So this, how we get this formula, you can refer back to chapter 3. Alright. Okay. Sample problem 4.9. Sample problem 4.9. 1 kilo of refrigerant R134A initially at 600 kPa and 25 degrees Celsius undergoes a process during which the entropy is kept constant until the pressure drops to 100 kilopascal. Determine the final temperature of refrigerant R134A, and the final specific internal energy. So that is the question. Okay, so sample problem 4.9. Okay, alright, so we are dealing with a refrigerant R134A. Okay, so basically you must know that which tables you need to refer. Okay, so it's in the okay, so the 1 kg in the mass given, mass 1 kg. Okay, and inlet P1 is 600 kPa. Okay, and also the T1 is 25 degrees C. Okay, and then P2 is 100 kPa. Okay, all right, so draw your tables. Okay, so here we are dealing with entropy. So basically it's better for you to draw a TS diagram, because if you are dealing with entropy, you got a straight line. Okay, so this is your bell shape. Okay, so first of all, check where is this location in the steam tables. Okay, so either it's in the superheated or mixture. Okay, okay, by referring to tables A12, so you know that 600 kPa, your Tsat 600 kPa Tsat is at 25.55 degrees Celsius. So which means that is T1 is 25, so it goes to superheated. Okay, so you need to refer to tables superheated. Okay, so from T1 25 degrees C, P1 is 600 kPa, so it's a superheated. So from that we can know the entropy. S1 is 0.9341 kilojoule per kg dot K. Okay, so this is from table, superheated table. Okay, so from here we know that, so this is your first point, somewhere here. So this is your point, superheated. Okay, and then this is a P600. Okay, so we got another 100. So P1, P2 is 100 kPa. Okay, so 100 kPa. Alright. Okay, so from this you can, as the process is isentropic. Okay, so because in the question telling us that the entropy is kept constant. Okay, so which means that it's a isentropic process. Okay, so S1 is equal to S2. Okay, so S1, S2. Okay, so at P2 is equal to 100 kPa. Okay, so you can check either it's in the mixture or superheated. So as we check, it's in the mixture. Okay, so your table will be something like this. This is your point 2 mixture. Okay, so process 1 goes to process 2. Okay, so the question is final temperature. So is as it in the mixture, so T sat, okay, so T sat is at minus 26.37 degree Celsius. Okay, and also for the lastly is a specific internal energy. Okay, so basically S2 minus SFG, okay, U2 minus UFG. So S2, you got your answers. So U2 kilojoule per kg. Okay, alright, thank you. Sample problem 4.10. Okay, sample problem 4.10. An isentropic steam turbine process 8 kg per second of steam at 7 MPa, which is exhausted at 75 kPa and 100 degree Celsius. 7% of this flow is diverted for other purpose at 700 kPa. Determine the power produced by this turbine and draw a TS diagram. So in this question, need us to draw a TS diagram. So we need to draw lah. Okay, so the diagram first. This is the body diagram. So we have a inlet here. Okay, so inlet is 7 MPa, so P1. Okay, and also we have mass m dot, okay, 8 kg per second. Okay, so this is your point 1. Point 2 is being diverted to 700 P2, 700 kPa. Okay, and P3, this is point 3. P3 is 75 kPa and T3 is 100 degree Celsius. Okay, so a diagram. Okay, so before we draw a diagram, so we must know what is the location. So this is a TS diagram. Isentropic is a one straight line, bell shape. Okay, first of all, we draw a 4 MPa. Okay, second. Okay, okay, so second is 0.7 MPa, 700 kPa, and lastly 75, which mean 75 kPa. Okay, so we got 3 lines. Okay, so we have, so from here we need to draw it's not draw, we need to determine the energy balance. So energy in is equal, minus energy out is equal to change in a system. Okay, so as we are in steady state condition, so the change in energy system is not transient, so it's zero, becoming zero. So energy in is equal to energy out. Okay, alright, so as we have two outlet from one source, Okay, so m dot h1 is equal to m dot h2 plus h m dot 3, m dot 1, m dot 3, sorry, 2, 3, h3. Okay, and also is a assuming is a adiabatic, no heat, no kinetic, and also no potential. So also we have the output. The turbine will produce output, work. So work out. Okay, so in general, work out is m dot h1 minus m dot 2 h2 minus m dot 3 h3. Okay, so mass balance. From mass balance, okay, because given in the question is 7% flow diverted, so which means that m1 is equal to 0.7 m2. Sorry, not 0.7, 0.07 m2. Sorry, m2 is 0.07 m1. Okay, so m2 0.07, 7% times the mass for it is 8 kg, 8 kg per second. So you can check. Okay, and another m3 is 0.93 m dot 1. Okay, because balance is goes to m3, so you got 0.93 m dot 1, sorry, 8 kg per second. So you got your kg per second, kg per second. So that is, so we have all the mass has been allocated. Okay, right. Then what info we have? So the only given direction is on 3.3 because it gives 2 points. So we can refer to tables. For point 1 and point 2, only one data given. So we cannot determine this location. So from this, from point 3, we can know the S3. So S is a isentropic, so it will have a straight line. So let's check what is entropy at point 3. Okay, so P3 is 75 kPa and T3 is 100 kPa. So either it's in mixture or superheated. So it's in the superheated. So directly from the tables, so you can know your S3. Kilojoule per kg dot K. Okay, so check either it's true or wrong. So check, you need to recheck either it's in superheated or in mixture. Okay, so from mixture interpolate, or if you don't have the, sorry, it's not kPa, degree Celsius, sorry, degree Celsius, 100 degrees Celsius. Okay, all right, so it's as it's isentropic, so S1 is equal to S2 is equal to S3. Okay, so from here, as we know this is at superheated, so we can draw line for point 3, something somewhere like this. So it's a straight line. Okay, so point 1, point 2, 0.3. So our TS diagram has complete. Okay. Alright. So let's come back. Okay. So we have then P1, okay, is at 7 MPa. So S1 is equal to S3 is equal to what amount? So by logically, it's as your S3 is in superheated, so normally this is also acts at superheated. Okay, so we can know the H1. From here also you can determine your H3 from tables, kilojoule per kg. Okay, and for P2 is P2 0.7 MPa. So unluckily 0.7, you need to interpolate. Okay, so S2 is equal to S3, so H2 kilojoule per kg. Okay, so total work, okay, work out m dot H1 minus m dot 2 H2 minus m dot 3 H3. So we have all the enthalpy, so we can substitute into your general equation. So we got the answer kilojoule per kilojoule, kilojoule. Okay, right. Okay, thank you. Okay, so how we want to interpolate between two pressure, between a pressure that does not display in the table A6. So table A6 superheated as previous example. So we got that the P3 is 75 kPa, okay, or 0.075 MPa. Okay, so because at the table A6 we have only 0.5 MPa, and also we have 0.1 MPa. Okay, so P3 is 0.05 MPa. Okay, so look at the temperature given is T3 is 100 degrees C. So look at 100 degrees C here. Okay, so firstly we want to know the S3. What is the value? So 0.1 MPa. Okay, so we got your S3 is 7.3611. Okay, so at 0.05 MPa, your S3, your entropy, 8.4489. Okay, so you can interpolate, and also this is your entropy, enthalpy 3, because we want to know what is the enthalpy. So at H3, okay, so at 0.1 MPa, the enthalpy is 2675.8. Okay, so here is 0.5 is 2682.4. Okay, all right. So we have this, so we can interpolate. Okay, so interpolate by using the pressure. Okay, so we have the bottom part is 0.05, so here we have 0.075, the upper is 0.1, so here is 7.361, sorry, bottom part, the entropy is 8.4489, so this is your S3, and the upper part will be 7.3611. Okay, so this is your part, this is your part. Okay, okay, alright, so pendek perpanjang, pendek perpanjang. Okay, so we got S3 minus the lowest one lah, because if you minus here, so you got negative. Okay, we want a positive value just because it's a ratio, so you can either do one. Okay, should be no problem. 7.3611 over 8.4489 minus 7.3611, and okay, so we got 0.075 minus 0.05 per 0.1 minus 0.05, so S3. Okay, similarly for enthalpy. Alright, okay, thank you. Isentropic efficiency of steady flow devices. So irreversibility inherently accompany all actual processes, and that their effect is always to downgrade the performance of devices. In engineering analysis, it would be very desirable to have some parameters that would enable us to quantify the degree of degradation of energy in these devices. An ideal device would be generally adiabatic and have no irreversibility. For example, an isentropic device. The parameter then expresses how efficiently an actual device approximates an idealized one is called isentropic or adiabatic efficiency. So isentropic efficiency are defined differently for different devices, since each device is set up to perform a different task. The isentropic efficiency is defined by comparing the actual performance of the devices to their performance under isentropic condition for the same inlet state and exit state. So basically, for actual performance, okay, normally the performance is much lower compared to work isentropic. Okay, so that's why we have isentropic efficiency. So isentropic efficiency for a turbine. The pressure difference for a typical turbine operational can be illustrated in enthalpy entropy diagram below. This is your diagram. So the isentropic work is the maximum possible work output that the adiabatic turbine can produce. Therefore, the actual work is less than the isentropic work. So this is your actual line. This is your isentropic line. So basically, your actual is much shorter compared to isentropic work. So a shorter divided by a longer process, we have the efficiency. So your efficiency, actual work divided by isentropic work. because for turbine, normally we assume that the work output from turbine is such amount, but in reality the work from turbine is much lower compared to the calculated one. So that is the isentropic efficiency comes in. Sample problem 4.11. Sample problem 4.11. Steam at 8 bar 550 degrees Celsius expand in a turbine to 0.01 megapascal. The isentropic work of the turbine is 1152.2 kilojoule per kg. If the isentropic efficiency of the turbine is 90%, calculate the actual work, find the actual turbine exit temperature or quality of the steam. Okay, so 4.11. Okay, so we have a turbine. Okay, so this is your in, this is your out. Okay, so given P1 is 8 bar, so you need to convert into kPa. Okay, so T1 is 550 degrees Celsius. So P2 is 0.1 MPa. Alright, and the work produced given directly is isentropic work. Work isentropic is 1152.2 kilojoule per kg. Okay. Efficiency given is 90%. Alright, so at the inlet, okay, so P1 8 bar is equal to 800 kPa, as 1 bar is 100 kPa, is equal to 0.8 MPa. Okay, and T1 is 550 degrees Celsius. Okay, check in the steam tables. So steam table 8 bar, as for P1 800 kPa, your Tsat is 170, so it's in the superheated. Okay, so check in your superheated. Okay, so I think it in superheated 0.8 bar. Okay, unluckily there is no 550 degrees Celsius. It's only 500 to 600. So you need to interpolate. So interpolate. Okay, so interpolate. What is your H1? Okay, and S1. Okay, alright, so okay, and then the actual work. Okay, actual work. Okay, so S efficiency is your work isentropic per work actual. Sorry, work actual per isentropic. Okay, so 0.9, 90%. Okay, work actual per isentropic 1152.2 kilojoule per kg. So work actual kilojoule per kg. Okay, alright, also from here, as we know that work actual actual is H1 minus H2 actual. Work isentropic H1 minus minus H2 isentropic. Okay, so the calculation is to find the actual exit turbine. So we have work actual H1 minus H2A actual. So H2A work turbine, this value H1. Okay, so H2A kilojoule per kg. Alright. Okay, then what else? The temperature. Okay, so at P2 given is 0.1 MPa and H2A is, okay, so you can check from steam tables. Okay, so from steam tables, as in the question state that quality of the steam, so which means that it's in the mixture. It's being given hint from the question. So basically it's in the mixture. So you can, from the steam table, so you can know the temperature. So Tsat. Okay. Alright, thank you. Isentropic efficiency of compressors and pumps. So the pressure difference of a typical compressor and pumps operational can be illustrated in entropy diagram below. So this is your diagram. So the isentropic work is the minimum possible work that the adiabatic compressor requires. Therefore, the actual work is greater than the isentropic work. Since efficiencies are defined to be less than 1, the compressor isentropic efficiency is defined as isentropic actual, because compressor require work in compared to turbine. Turbine produce work. Compressor require work in order to be working. So basically, in reality, okay, so the amount of work required is much more compared to the calculated one. So that is, we call it as a isentropic efficiency. So for compressor, so H2 S is isentropic, enthalpy 2 isentropic minus H1 divided by H2 actual minus H1. For a pump, okay, pump compared to compressor, normally compressor dealing with air. Okay, in order to transfer liquid, we use a pump, and normally pump cannot operate under the mixture condition. So pump normally operate at a compressed liquid condition normally. But who knows, in the future, maybe one day people can design a pump that can operate for both, which is the combination of liquid and gas, a mixture. Okay, so operate for a pump. I don't know. But for currently, a pump normally operate liquid only. So that's why for the isentropic work, so we have your volume, specific volume, change in pressure divided by actual work, H2A minus H1. So that is for efficiency, isentropic efficiency for pump. So how we get this? You can refer back to chapter 3, pump. Sample problem 4.12. Sample problem 4.12. Air enter a compressor and is compressed adiabatically from 0.1 MPa megapascal 27 degrees Celsius to a final state of 0.5 megapascal. Find the work done on the air for a compressor isentropic efficiency of 84%. Assume constant specific heat of air at room temperature. Okay, so we 4.12. Okay, 4.12. Alright, so it's a compressor. So compressor work in. Okay, so we work in. So this is your inlet. This is your outlet. Okay, so given in the question that P1 is 0.1 MPa, T1 is 27 degrees Celsius. Okay, and the final state P2 is 0.5 MPa. Okay, right. So find the work done. Okay, so here we need to do a energy balance. Okay, so energy balance. Okay, so we have Q in plus Q in plus work in plus kinetic plus potential, okay, is equal to Q out plus we have M H1. Okay, Q out plus work out plus M dot H2, okay, plus kinetic plus potential. Okay, so we take out the kinetic and potential because assume is negligible and it's a adiabatic. Okay, so adiabatic compression stated in the question. So adiabatic, no heat transfer. As compressor require work in, so work out is negligible. So left is work in, mass. So work in plus M dot H1 is equal to M dot H2. Okay. Alright, so rearrange work in is equal to M dot H2 minus M dot H1. Okay, so here we can rearrange again, and we are dealing with air. So air, normally air. Okay, so the enthalpy of air is M, okay, Cp T2 minus Cp T1. Okay, so take out, so we have M dot Cp T2 minus T1. Okay, alright. Okay, so here as we are dealing with air, so what do we need? Okay, so the temperature T2, because we want to find the work done, so T2, so T2 over T1, because we have only pressure, So is equals to P2. Okay, this is isentropic. So P1. Okay, so K minus 1 over K. Okay, so T1 we got T1, P1, P2. This is isentropic S. So T2S degree Celsius. Okay. Okay, and then okay, so we got the isentropic work isentropic m dot Cp T2S minus T1. Okay, Cp for air, Cp you can refer to tables, tables A-2, I think A-2 something. So 1.013 kilojoule, something kilojoule per kg dot C or K. If C, you don't need to change to Celsius. If K, Kelvin, the unit Cp, Kelvin, you need to change this to Kelvin. Okay, so check again. I don't remember the units, so you need to recheck what is the units. Okay, and the value Cp. So substitute Cp. Okay, and the mass flow rate is it given? No. So work Cp T2S minus T1. Okay, so as your transfer mass to this side, so this we have a kilojoule, so we have transfer the mass, so the unit is kilojoule per kg. So because we have transferred the mass at the left side. Okay, so Cp, so you got units kilojoule per kg. Okay, alright, so that is the work done, work isentropic. This is work isentropic. So actual work. Okay, so actual work. So the efficiency for compressor, so work isentropic over work actual. Okay, so in the question given that the efficiency is 84%, so we got 0.84 work isentropic. We got, what is your value, divided by work area. So work actual, kilojoule per kg. Okay, alright, so thank you. Sample problem 4.13. Sample problem 4.13. A pump is used to draw a refrigerant 134A at minus 30 degrees Celsius and 100 kPa to 360 kPa. If the efficiency of the pump is 85%, determine A. Isentropic work, B. Actual work, C. The enthalpy of refrigerant 134A after the pump. Okay, so 4.13. Okay, so we are dealing with a pump. Okay, so this is your inlet, this is your outlet. Okay, so given inlet P1 is 100 kPa and T1 is minus 30 degrees Celsius. Okay, Okay, and also the P2 360 kPa. Okay, so T2 have not been mentioned. Okay, bear in mind, pump normally used for compressed liquid. Okay, so basically pump cannot operate in a mixture condition because pump cannot deal with a mixture. Okay, if there is air or something mixture air in the liquid, so we call it as a airlock. Okay, so basically normally pump operate at liquid 100%. Okay, alright, so that is a normal condition. Okay, so we need to recheck as we are the question is isentropic work S. Okay, so we need to know what is the S value here. Okay, so the efficiency of pump. Okay, so S efficiency for pump is V P2 minus P1 is a constant volume. Okay, pump operate at constant volume. Okay, so this is at isentropic condition. Okay, isentropic condition at constant volume. Okay, so the actual will be H2A minus H1. Okay, so we need to find what is the volume first. Okay, so specific volume for pump. Okay, so at P1 100 kPa and T1 is negative 30 degrees C. Okay, so this is at check at refrigerant. Normally is at a mixture. So using this at T1 sat, okay, 30 degrees Celsius. So V1 specific volume, okay, F, okay, meter cube per kg. Okay, alright, so we have from tables, so we can calculate the work isentropic. So work isentropic is V P2 minus P1. So V P2 360 kPa minus 100 kPa. So this is a meter cube per kg. Okay. Okay. So what is your final answer? So bear in mind you have meter cube per kg, okay, times kPa. So kPa is equals to kilo kg per meter dot second square is also equals to kilojoule per meter cube. Okay, so substitute we use here to integer question, so we got the answer is in kilojoule per kg. Okay, alright, so we have determined the isentropic work, so we can calculate the actual work. So the efficiency is work isentropic over work actual. Okay, so given the efficiency is 84%. 85%, sorry, 85%. 85%. So 0.85, what is your just now divided by work actual. So work actual kilojoule per kg. Okay, so that is the actual work. So just now you have calculated the isentropic work. Okay, alright, so work actual is also H2 actual minus H1. Okay, so H1 just like before. Okay, so you have determine, so determine also your H1 at F, saturated liquid. Okay, what is the value? Kilojoule per kg. Okay, so from steam tables you can know H1 is HF at minus 30 degree Celsius. Okay, so H2A kilojoule per kg. Okay, alright, thank you. Isentropic efficiency of nozzle. So the pressure difference of a typical nozzle operational can be illustrated in a diagram below. Okay, so the nozzle efficiency can be written as, so this is your efficiency actual divided by isentropic. Okay, so this is your actual, this is your isentropic. So from energy balance equation for steady flow, no work, because it's a nozzle produce no work and also require no work. Neglecting potential energy and conservation energy for the nozzle, we have this equation. This is from general energy balance. And rearrange, we got this equation. So therefore, the nozzle efficiency can be used something like this. This is the nozzle efficiencies. Okay. So normally for nozzle the inlet velocity is too small, it can be neglected. Okay, because at nozzle the inlet velocity normally too small, so neglected, we consider it 0. Then the nozzle efficiency can become this equation. We only consider at a final state. Sample problem 4.14. Sample problem 4.14. Air at 200 kPa and 950 Kelvin enter an adiabatic nozzle at low velocity and is discharged at a pressure of 110 kPa, kilopascal. If the isentropic efficiency of the nozzle is 92%, determine A, maximum possible exit velocity, B, the exit temperature, and C, the actual exit velocity of the air. And assume constant specific heat of air at room temperature. Okay, so here we know that we are dealing with 4.14. So we are dealing adiabatic nozzle. Okay, so inlet 200 kPa, P1, T1 is 950 Kelvin, low velocity, V1 near to 0, okay, and P2 110 kPa sorry, okay, efficiency is 92%. Okay, alright, so this is no nozzle. Okay, so maximum possible exit. Okay, possible max velocity V2. Okay, alright, so from energy balance, okay, so energy balance, okay, so I have simplified. So H1 plus V2 1 over 2 is equal to H2 plus V2 power of 2. Okay, so energy balance, this is I have taken out, pump. So this is the leftover. Okay, so what we need is enthalpy. Okay, so enthalpy as H1 Cp T1 H2 Cp T2. Okay, so T1 we have been given directly, T2. Okay, so T2 we can calculate. Okay, so S this is a isentropic. Okay, so this is S. Okay, alright, so using T2S over T1 is equal to, as we only have pressure, so P2S over P1 K minus 1 over K. Okay, so T1 150, P1, okay, so P2S, this is isentropic. Okay, so this is your isentropic also. Okay, so you can calculate. So T2S is Kelvin. Okay, alright, so you can substitute this value into this equation. So you can get V2 is 2 Cp T1 minus T2. Okay, so T2S, sorry. Okay, you got your value T1 given directly in the question. Cp, check in the tables, 1.0 something. Okay, tables A2. So you got your value meter per second. Okay, so that is the max possible velocity. Okay, B, exit temperature has been calculated. Okay, alright, so C, actual velocity. So as we have calculated before, this is the only isentropic. So the efficiency work actual over work isentropic. Okay, so we got actual H2 minus H1 over H2S minus H1. So you can change Cp T2 minus T1 over Cp T1 minus, okay, sorry, vice versa. So sorry, H1 minus H2. Okay, you got negative. Okay, so this H1 minus H2S. So we got Cp T2 H1 T1 minus T2 actual, this is your actual, divided by Cp T1 minus T2S. Okay, Cp you can take out. Okay. Okay, so we have calculated, this is your T2S. Okay, so knowing your here, we can calculate the T2A. So efficiency is T1 minus T2A over T1 over T2S. T2S has been calculated, T1 given directly. So the efficiency is 0.8. Efficiency is 92%. So 0.92. Okay. So T2S is Kelvin. Okay. And also what else? The actual velocity. Okay, so the actual velocity, so efficiency V2A divided by V2S power of 2. Okay, so we have calculated the V2S. Sorry, this is V2S. V2S, because you are dealing with entropy. This is also isentropic. Okay, so V2S we got. So we have V2S is efficiency 0.92 times V2A power of 2. Okay, so you got your meter per second. Okay, alright, thank you.